Today we are going to learn how to obtain stress concentration for a plate. Now, before going to our stress concentration, let us know what is the stress and how the stress concentration is occurring and what are the factors that affect the stress concentration, and then we will go for modeling for the stress concentration using ABACUS. So stress is your force by area. So if we have a bar, like this, and if we apply some load here, and this side we used to make fixed. So force by that cross-sectional area is your stress, which is denoted by sigma. Now, if we have a bar like this, we see that how the stress is flowing. The stress flow, you see how the stress flow, you'll observe that how the stress is flowing in this member due to the applied loading. You'll observe that there will be some stress concentration this end, and thereafter you'll observe that stress is basically following like this. Stress is following like this. And after some distance, we'll observe. After some distance, we'll observe the stress is uniform in this zone. Now, probably you can recall that while doing some tensile test, we used to measure our data. So, why we used to measure in this middle zone? Because in this zone, stress used to be uniform. And in this case, and in such cases, we'll observe that failure of the material used to occur either in this middle zone or near the support. Many cases you will observe there is failure in the near the support because stress used to be high here. Okay. And in such cases, we used to reject the sample. We used to reject the sample and we used to consider those sample which basically fell in this zone, so that we make sure that stress is uniform here, and whatever the data we are measuring here, the data is coming due to your uniform stress in this zone. Now, if you consider your dog bone sample, in the dog bone sample, you will observe that we used to have a cross section like this. We used to have a cross section like this. Have a cross section like this. So now, if we apply load here, we'll observe the stress basically used to follow like this. Stress used to flow like this, and in this zone, we used to have uniform stress, and we used to measure the data here. Cross section like this. Okay, and if we do the testing, if we have a cross section like this, and if you do the testing, you will observe that many cases the failure is occurring in this zone. Many cases the failure is occurring in this zone because there will be huge stress concentration in this zone because of the change in the cross section. This is your A and this is your small a. There is a sudden change in the cross section. There is a sudden change in the cross section. So stress concentration will be higher and material will fail in this zone. Okay. Now you will observe that we used to make a dog bone sample. We used to test it. So in the dog bone sample, what we used to do? We used to do the smooth transition like this, and we used to do the testing. So once in the dog bone sample, what we used to do? We used to fillet it, or you can say we used to make that change in the cross section in a smooth manner. We used to change the cross section. We used to make the change in cross section in a smooth manner, so that stress flow will be uniform in this zone, and the stress concentration that was occurring, we used to minimize the stress concentration here, and we can avoid the sudden failure in this zone. So what we have learned, that stress is basically your force by area, and stress concentration used to occur when there is a sudden change in the cross section. Now you'll observe in many design or in many analysis cases, we need the maximum stress. We need the maximum stress so that we can safeguard our structures. We can apply some factor of safety and we can design our structures. we can find that maximum stress by applying some factor. That factor is basically known as your stress concentration factor. What is the stress concentration factor? Stress concentration factor is your maximum stress divided by your average stress. The average stress that is occurring in this zone. Okay, that is known your stress concentration factor K. So what we are doing here, we are basically simplifying our analysis procedure. Once we know that what type of hole we have, whether we have circular hole or we have an elliptical hole, what type of hole we have, depending on that, we can find that what is the stress concentration factor. Once we find what is the stress concentration factor, you can find our maximum stress, which is our primary interest for design, so that we can apply some factor of safety there. Now again, you will observe, though stress is basically depend on the material property. Stress, that your stress is equal to force by area. Okay, the developed stress in the structures that also basically depend on that your property of the material, that is equal to here. The stress is basically force by area. Again, how much stress will develop, how much stress, this is your applied load, you can say applied load or applied stress. Okay, this is your applied stress. If sigma is equal to P by A, in that case, this is applied stress, and stress developed in the structures that will depend upon your how much elongation is occurring and what is the modulus of elasticity. So this part is your property of the material. So though stress is a function of material property, stress is a function of material property, but the stress concentration factor, is a function of geometry and the type of discontinuity we have, whether we have a circular hole, whether we have an elliptical hole, or we have a connection like this. So basically, what type of discontinuity we have and what type of geometry we have. Geometry in the sense how much width of the plate we have, how much diameter of the hole or cutout we have. Depending on that, we can have our different stress concentration factor. So stress concentration factor is basically function of geometry, not the function of material property. Stress is a function of material property, but stress concentration factor is a function of geometry and what type of discontinuity we have. Okay. So now, if we have a plate and if we make a cutout like that, we will observe that stress is very high in this zone. Stress is very high in this zone. If you have a plate and you are applying like load like this, you will observe the stress is very high in this zone. So here you can observe that stress is concentrating in this zone. Now, if you want to plot, you will observe that stress, the magnitude of the stress will be high here, magnitude of the stress will be high here, like this. And if you go away from the opening part, you'll observe the stress is basically changing like this. Stress is basically changing. Basically, you will observe that the stress concentration, stress basically is coming like this. This is the red part, is that magnitude is high here. If you see the magnitude, and if you plot this red magnitude, this one 2.73, and then if we plot the green one, 1.55, okay, 1.55, here 2.73, and here blue one is basically something nearly 1.37, like that. If you plot that value, you will observe that stress will be like this. It will be like this. From this side also will be like this. Okay, so here what we have seen, that stress, change in the stress, if we have a plate with a circular cutout, and if you apply the load, this circular part will be elongated and it will look like ellipse. That's fine. And here there will be high stress concentration, and if you go away from here, you'll observe the stress, magnitude of the stress basically varying like this. Magnitude of stress is varying like this. This is basically, this colorful pattern is showing what are the different kind of stress we have. Okay, so if we plot the magnitude, it will look like this. So this is what all about. This is all about stress concentration and that factor affecting the stress concentration. Now here, if we Now here we'll see what is the stress concentration factor for elliptical cutout, and next we'll discuss what is the stress concentration for a circular cutout, and again we'll discuss how stress concentration is affected by our change in the cross section. So here, if we observe that if we have a plate and we cut out, in that case, our stress concentration factor can be written like this. Stress concentration factor K, that is equal to maximum stress that is occurring in this zone, and average stress that is occurring here. Average stress basically the total load P divided by W minus D diameter of the hole, D diameter of the hole into T. That is your average stress, sigma average. Okay. Now, if you know average stress and if you know what is the stress concentration factor, then we can find how much stress is occurring here. Okay, so if we have a plate with elliptical cutout, in that case, stress concentration factor we can write as a 1 plus 2b by A. So B here, your B here, basically 2b is here, your minor radius of the ellipse, and 2a is your major radius. Okay. Now stress concentration factor K, that is equal to 1 plus 2b by A. Now if it become a circular, in that case you'll observe that your B is equal to A. Okay. And if you put, you'll observe that if you have put that B is equal to A, so this will get cancelled out, there will be 3. So stress concentration factor will be 3. So here what will happen if we have a plate with circular cutout, like this, in that case your maximum value of stress concentration factor will be 3. Maximum value of stress concentration factor for a circular cutout will be 3. Okay, now here if we concentrate on your, if we consider stress concentration factor with elliptical hole, that again can be simplified like this. The stress concentration factor for elliptical cutout can be written in this form, that is equal to 1 plus root under A by rho. Root under A 1 plus root under A by rho. Okay, so A is here, that is half of your major axis, and rho is basically local radius. Rho is basically local radius of the curvature at the foot of the elliptical hole. So this is basically your rho. So now here we just see if the value of rho is small, then we used to have a high stress concentration factor. If a value of rho is very small, then we'll have a high stress concentration factor. If value of rho is high, in that case, high like this, in this case, we can have a low stress concentration factor. So high stress concentration factor, that means we will have a high stress in this zone. Low stress concentration factor means we will have a less stress that is concentrated here, and that will be low. Okay, so what we have learned, that for elliptical cutout, stress concentration factor is like this. Okay, that is again property of our geometry, not the property of your material. Stress concentration factor is a property of the geometry of the plate. Again, we have learned that stress concentration factor will be high if we have a low local radius of curvature. In that case, our stress concentration will be very high. Okay, so we have learned that our stress concentration factor is independent of the material property and is dependent upon the property of the geometry, and also depend upon what type of discontinuity we have. If we have a local curvature, if we have a local radius of curvature of low magnitude, then we'll have a high stress concentration there. Okay, so basically the size of R, or basically size of rho, the size of rho of the discontinuity decreases, then stress concentration will increase. So basically, if we have a small local radius of curvature, okay, in that case, a higher rho, in that case, if you have a higher value of this rho, in that case, our stress concentration will be low. Okay, now if we, so this again, this part, again, this theory, the theory that we have discussed here, basically for infinite plate. This theory is basically infinite plate. Now, in real life, we used to have a infinite plate in the sense if you have very large plate and we have a small hole cut out there. In that case, this theory is very well suited. Okay, infinite plate in the sense if you have a very large plate, but if you have a finite plate, okay, we have a definite length of the plate, definite width of the plate, definite thickness. In that case, we will observe our stress concentration that is basically depend upon the ratio of D and the W. Stress concentration can be written in this form. So here again, you just see that what is the diameter of the cutout, what is the diameter of the cutout, or what is the width of the plate. Depending on that, our stress concentration factor is to vary. Okay, so if we have a finite plate where we have a finite length of your W, finite length of the W, in that case, our stress concentration factor can be written in this form. Again, you can see that if we know what is the value of your D by W, the value of D by W, from this graph, you can have the data. So here, if you plot it, you will get the value as you have 2.51 like this, nearly 2.5. Stress concentration factor will be 2.5 like this. Okay, and from that we can find what is the maximum stress occurring in this zone. Okay, now if you have a section, rectangular section or circular section in which there is a sudden change in the cross section. If you have a rectangular section or circular section and there is a sudden change in the cross section, in that case, stress concentration factor is to vary in this form. So again, this stress concentration factor is to be function of R by H as well as your W by H. R by H, basically R here, basically R is here, your local radius of curvature. R is here, local radius of curvature here. Okay, so stress concentration factor is to depend on the factor of R by H and ratio of W by H. Okay. Now, if you know what is the R by H for you, and if you know what is the W by H for a particular sample, in this case, you can find the value of stress concentration factor for your plate or for your sample. And again, for this case also, maximum value of stress concentration factor will be 3. For this case also, maximum stress concentration factor will be 3. The maximum value of the stress concentration factor will be 3. And that value can be reduced if we have a smooth curvature here. If you have a smooth curvature here, then we'll have a reduced value of the K. Now, question is that how to obtain the K experimentally? How to obtain the value of the K experimentally? How we can obtain it through some experiment? Use photoelasticity. In the photoelasticity, what happened? You used to have a sample. We used to have a sample, and we used to stress it, and then we used to pass a monochromatic light. We used to pass a monochromatic light. So in the monochromatic light, we used to have a single wavelength. That is why it's called a monochromatic light. It should have a single wavelength. When it passes through a medium which is under stress, in that case, it is to create different. It is to create different wavelength. It is to create different wavelength, and that is to reflect as a change in color. That is to reflect in change in color. Okay. So in the photoelasticity, we also can find what is the pattern of the stress concentration. Now, if you place some strain gauges here, okay, if you place some strain gauges here, you can measure the stress that is occurring here, and if you place some stress here, the strain gauges here, and here, you can measure the stresses and we can plot it. Okay, so one is you're using your photoelasticity. But again, in that case, that material should be transparent so that light can pass through. And if you have a very solid material and it is not transparent, in that case you have to rely on your strain gauges. So if you have a plate and you just place strain gauges here, 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 and here, some different distance, and you measure the strain, and you know that a strain is related to stress like this, and we can find the stress. So if you have a strain gauges, you can measure the strain, and from there you can convert the stress and you can plot it. It will come. If you have a circular cutout here, the stress will come like this. Okay, so we have a photoelasticity test. We have a strain gauge that we can measure the strain, and from that we can find the stress, and from there we can find the stress concentration. Or in some brittle material, we can use brittle coating method to find the stress concentration. So these are the way through which we can find our stress concentration factor through some experimentation. Now thing is that these processes are very time consuming, laborious, and costly. These processes are time consuming, laborious, and costly. So alternatively, what we can do nowadays, fine element method is developed very well. And if we are able to model it in some fine element software, and if we see, you can have very reliable data of your stress concentration, and from there we can find the factor and which you can further use for your design purpose. So here we have alternate way, that is your fine element method, but that is not experiment method, that is your numerical method through which we can find the stress concentration. Okay. Now here till now what we have discussed, that what is the stress, what is the and affecting it, and how we can find it. Now here we will discuss how the stress concentration is affecting a ductile material, and then again we'll discuss how the stress concentration is affecting your brittle material. How a ductile material is behaving under stress concentration, and how a brittle material is to behave under stress concentration. If you see a ductile material, and if there is some stress concentration, you will observe that stress concentration is neglected. You will observe that stress concentration, the effect of stress concentration is neglected in case of ductile material. So what happened if we have some material? So here initially there will be some stress concentration in this zone, and this zone material, the material here, which is here, will reach to your yield value first. You will reach to real yield value first, and once the material is to yield, you'll observe that in case of ductile material, we used to have a plastic flow. We used to have a plastic flow. So what happened here, when the stress used to, when the stress acting here, the stress develop here is yield first, then nearby material also also gradually reaches the yield value. Again, further increasing in the load, lead to the yielding of full cross section. So what are the stress concentration was developing here after yielding? What happened, that used to mitigate, and whole zone used to yield. Okay, so whatever the stress concentration was occurring here, that is to mitigate after some times. So since it is to mitigate and it is to distribute throughout that whole cross section, whole effective cross section, so stress concentration never become a burning topic. Stress concentration for a ductile material, stress concentration never become a big problem. Okay, now if we come to brittle material, you will observe the brittle material. You will observe, if you try to plot that failure of the brittle material and the stress developed in the brittle material, you observe that initially strain used to change gradually, stress strain behavior it will change gradually, and there is sudden failure like this. Okay, so brittle material, what happens? Stress concentration become a big factor. So in ductile material, stress concentration is not a big factor, but for your brittle material, stress concentration it become a big factor, because once it reaches that maximum stress, once it reaches that air failure stress, thereafter suddenly crack is to appear, and the cracks propagate very suddenly, and there is to failure of the structure. So concentration become a big factor, and here the stress concentration, the stress that was developing in that zone, never get a chance to mitigate. Okay, never get a chance to mitigate, because once it reaches that ultimate stress, suddenly failure is to occur, and stress do not get a chance to mitigate. Okay, so in case of brittle material, stress concentration is to be a big factor. Okay, here in our computational laboratory class, what we are going to do, we are going to analyze a plate with a circular cutout, and material property we will consider as a isotropic case. Here you just see it is 200 GPa, that is your property for ductile material. So here we are going to perform a linear analysis of a plate having a dimension of 50 mm and 100 mm, and having a cutout of 10 mm at the center. So now if we calculate the D by W ratio, that is coming as your 0.2. Now if you want to find what the stress concentration is occurring, what is the stress concentration is coming, then we have to draw a line, and we have to find how much stress concentration factor is coming. So theoretically, that stress concentration factor is coming as your nearly 2.5. Okay, so here I have considered 2.51. And if we know that what is the average stress is acting, that you can calculate, in this zone. You can calculate in this zone. At average stress, that will be your P divided by W minus D. Again, you have to divide it with the thickness. So P is here 100 Newton into your length 50 mm. That much load is acting there. And here W is your 50 minus 10 is the diameter of the cutout. So once you calculate this one, again you have to divide it with the thickness. So if you do it, you will get that average thickness that is acting in this zone is your 12.5. Now there is a cutout and we are applying the load, there will be stress concentration, and maximum stress that will occur theoretically the maximum stress that will occur is your 31.375. So maximum stress that will occur here, that will be 31.375. Okay. Now if you want to find how much stress is occurring along this one, that you can find. Okay, if you do that or numerical modeling. So here you have to select the node and you can find how much stress is occurring, and you will find that the stress is coming like this. Okay, so what we are going to do here, we are going to analyze a plate with circular cutout, and we'll see that how much maximum stress is coming. Theoretically, this much stress should occur, and as per our numerical model, how much stress is coming, that we'll try to see, and we'll try to find the stress concentration factor also. And you also try to see whether you are getting this type of stress pattern or not. Okay, this stress is at particular loading, and once you increase the load from P1 to P2, you should get a stress pattern like this. Okay, and this stress is for y direction. That stress is for y direction. How much stress is acting in the, that is acting in the y direction. So here, what we are doing, we are going to model a plate with cutout considering ductile material, and we are going to perform linear analysis. Now here you have to keep one thing in your mind, that in the linear analysis, whether you consider isotropic material or orthotropic material, you are not going to get the real behavior which is to occur during failure. Once here, what we can get, we will get a stress pattern but you will not get the real behavior which is to occur during the failure. To model that, you have to go for nonlinear analysis. So if you model a nonlinear analysis for ductile material and for brittle material, then only you will get a different stress pattern and different behavioral pattern. Otherwise, you will get similar stress pattern if you use ductile material or if you use brittle material using linear analysis. If you perform linear analysis, in that case, you will get similar stress pattern. One thing can happen, and for orthotropic case, stress pattern may be different because in your orthotropic case, your E1, E2, and E3, G1, 3, G3 are different. In that case, you may encounter with complex stress distribution. Okay, you may encounter a complex stress distribution because E1, E2, G1, 2 all are different. So in that case, you may encounter a complex stress distribution. You may encounter a complex stress distribution, but you are not going to get the real failure pattern. To do that, you have to model it. Have a real failure pattern. In that case, you have to go for nonlinear analysis for ductile material and for brittle material. So thing you have to keep in your mind that ABAQUS do not have any inbuilt unit systems. So what you have to do, you have to consistent with the unit. If you are modeling your geometry using meter and all the force in Newton, in that case, you should enter the density in kg per meter cube, and as output you will get the stress. You will get the stress in Pascal unit. Now, if we consider all the geometry in mm, and if you consider all the force in Newton, then you have to define the density in ton per meter cube, and output, the stress output that you will get, that will come as a megapascal. So you have to interpret in that way. So either you can use this unit systems or you can use SI unit system in mm. But you can use any other unit systems, but again you have to be very consistent. So most popularly we can use either this one or this one. Okay, so for this analysis we'll see how we can use these unit systems and how we can interpret our result. Now what I was discussing, that initially what we're going to do, initially we'll learn how to model a plate with single cutout, and then we'll try to learn how to model a plate with a multiple cutout. Again, we'll see if we arrange the cutout in a particular manner, you'll observe that your stress concentration factor is reducing. Basically, our maximum stress that will develop will be lower than our single cutout. Okay, so we'll try to see how much maximum stress is coming. And if we arrange in this pattern, then how our stress pattern is coming. So next, what we're going to do, next we are going to model a plate where there is sudden change in the cross sections, and this cross section initially we will consider as a rectangular section, and we'll try to see how our stress concentration factor is affected by R by H factor and your H by W. How our stress concentration factor, or how our maximum stress is affected by with the R, how our maximum stress is affected by the R parameter, or how our maximum stress is affected by R by H and H by W parameter. That we are going to see. And next, we will see how we can define material property in nonlinear analysis, and also try to see.